In this project, we explored how to train small language models to perform reliable, structured reasoning using Tunix. While large language models already reason well, they are expensive and hard to deploy. Small models, on the other hand, are efficient and practical, but they often fail at long-form reasoning, get stuck in loops, or hallucinate intermediate steps. Our goal in this hackathon was to close that gap and show how Tunix can be used to train compact models that reason in a controlled and useful way. Our training strategy follows a cold start approach, which is critical when working with small models. Instead of jumping directly into reinforcement learning, we first perform supervised fine-tuning on carefully curated reasoning traces distilled from larger models like DeepSeek-R1 and Qwen32b. This stage teaches the model how to structure its reasoning, how to follow strict output formats, and how to avoid common failure modes such as language mixing or repetitive loops. In practice, this supervised phase acts as a structural prior that makes reinforcement learning both more stable and more effective. Once this foundation is in place, we move to reinforcement learning, but not with traditional binary rewards. Instead, we implement reinforcement learning with reference probability reward, or RLPR, using Tunix's GRPO framework. The key idea is to avoid rewarding the model only when the final answer exactly matches or partially matches the ground truth. In reasoning tasks, that signal is often too sparse and does not reflect the quality of the reasoning itself. A model can guess the correct answer with bad logic or produce good reasoning and fail due to a formatting mismatch. With our LPR, we instead reward the model based on how much its reasoning increases confidence in the correct answer. Concretely, after the model generates a reasoning trace, we measure the average token level probability it assigns to the ground truth answer, conditioned on that reasoning. This gives us a dense, smooth reward signal that directly reflects whether the COT is actually useful. To avoid shortcut learning, we debias this reward by subtracting the probability of the correct answer when the model answers directly without reasoning. This isolates the true contribution of the reasoning steps and penalizes verbose or irrelevant chains. Training stability is a major challenge in reinforcement learning for small models, so we applied several techniques described in recent RLPR paper. We filter out prompts with extremely low reward variance, which are either too easy or too hard and tend to introduce noisy gradients. We also use a two-level format reward, a strong exact match reward for perfect tag adherence, and a softer shape and signal that encourages correct structure while penalizing repeated or missing tags. Tunix supports a range of post-training techniques such as fine-tuning, reinforcement learning, and distillation, offering developers a practical path to building efficient deployable reasoning models.